Hello and welcome to the first video in this series. In these video lectures we will endeavour to summarize the following topics. Firstly, functions. What are they and how to describe them? Next we will describe how we can analyze the rate of change of these functions through a process called differentiation. And finally we will look at methods to approximate functions such as the Taylor series method. In these videos we will utilize visualization methods such as graphing in order to develop an intuitive understanding of functions and the analytical methods. For example, we can look at the cosine function and visualize it over a domain from -1 to 1. We can also look at the rate of change of this cosine function, which is minus sine, and indeed we can look at approximating this cosine function as a short polynomial around x equal to 0. Here in this first video we will look at how we can describe functions in terms of their general features, but first let's look at how to define what a function is. Functions are the primary tools used in mathematics and indeed comprise the majority of physical models. A function is a process of association. In maths we can associate numbers from one set to another, and indeed in physics typically associate values of some variable like position to another variable like time. This process of association can be visualized using a mapping diagram. For example, here we're mapping values from a set called x to values in a set called y. The process of mapping is described by this abstract notion of a function, and here we've called it f. The set y is typically referred to as the dependent variable, and it depends on the initial set x, which is referred to as the independent variable. The dependent variable y is a function of x, which in this case is simply x squared. This association is also referred to as a process of mapping in mathematics, such that functions map elements from one set to another set, or indeed mapping from some domain to some range. Notation-wise, you might see it as written as f(x) mapped onto y, and the domain is all the values of the input which produce a valid output. That is, an output that is not infinite or imaginary. The range then is all of these possible outputs, and on a graph we can sometimes visualize these functions by placing the domain on the horizontal axis and the range on the vertical axis. Mathematically we can define the domain and the range using either inequalities or using set notation. Here in this example, the domain x includes all the real values between -infinity and infinity without including infinities, and the range extends from 0 up until infinity. Using set notation, we can use the round brackets to indicate up to the value and a square bracket to include that value. The large E-like symbol indicates that x is an element of this specific set. The process of mapping in a function can be defined as either one-to-one mapping, such as in the case of f of x is equal to x cubed, and here each value of y is associated with a single value of x. If we take any value on the x-axis, it will be mapped onto a single value in the y-axis. Alternatively, the function may be a mapping from many to one, such as in the case of f of x is equal to x squared, which is the example we used in our mapping diagram, which is a 2-to-1 mapping, such that each value of y can be mapped onto two values of x, as in the case of y is equal to 9. To be defined as a function, the mapping must be unique. You cannot have multiple values of y mapped onto a single value of x. For example, in the equation of a circle, we can see that this is not a function because when we look at the mapping, we can see that a single value of x produces two values of y. And hence, the equation is not an explicit function. If we look at how we can apply all this to physics, we first need to recognize that in physics we measure quantities such as space, time, and energy. We associate these quantities as variables. and we define the dependencies between these different variables using functions. For example, the kinetic energy of an object with some mass is a function of its velocity, and we can write this mathematically by stating that the quantity energy depends on the value of v, velocity. The function then is the expression defined as a half mv squared. And we can visualize this function as a curve, which associates values of energy to values of velocity. Next, let's look at how we can describe functions in general. The relationships between different variables are typically defined within a mathematical or algebraic equation. The way in which the dependencies of the different variables upon one another are defined in the equation depends on the functions. Many such equations will have the function explicitly stated in terms of the dependent variable x. For example, we can see this equation has y is equal to x squared minus 5x. And hence the function is obvious. We don't need to do a lot of work to see how y depends on x. This is not always the case, however, and in many examples, the dependencies between the two variables are not explicitly stated. A simple example of this is the equation of the circle, where x squared plus y squared is equal to 1. The question is, what is the function here? We can say here that the function is implicitly defined within the equation, but we need to solve for y in order to have the equation explicitly tell us what the function is. In solving for y, we determine that y is equal to the root of 1 minus x squared, and that there are two solutions, a positive and a negative solution. And indeed, the unit circle equation has got two functions hidden within it. One defines the positive, or the top of the circle, and the other defines the negative semicircle. So in such explicit examples, we have to do a little bit of work in order to define explicitly what the function is. Another type of situation is when we have multiple dependent variables, such as x and y, both depending upon another variable or a parameter. Such parametric functions are typically found whenever we define conic sections such as circles or ellipses. And here we can give another example of a conic section called a hyperbola, where the x point is defined in one equation and the point in y is defined in another equation, and both of these are dependent variables depending on some parameter called t. And if we vary t over a range such as from minus 0.1 to plus 0.1, we can calculate the value of x and the value of y, and if we visualize these values, we can see a hyperbolic curve over a certain range of x and y. For typical functions, we can map values from the domain x to some range y using y is equal to f of x. Can we instead map values of y to values of x? To do so, we have to define the inverse function, and typically this is quite straightforward. Let's determine the inverse function for a simple case of y is equal to x cubed. The first step is to transpose the equation by solving for x. If in the original equation y is equal to x cubed, then transposing this we will solve for x, and we will determine that x is now equal to y to the power of 1 over 3. Next, we swap the two variables x and y. And here now we have y is equal to x to the power of 1 over 3. This then now has our inverse function defined, and we can label this inverse function as uppercase f. In this example, we see the blue line being the original function and the red line being the inverse function. There is an obvious symmetry here, and it's defined by the line y equals to x, this 45-degree line, such that the inverse function is merely the reflection of the original function through this line. Indeed, this is just equivalent to swapping the position of the x and y axis. Next, let's look at other symmetries that functions may share. Indeed, it can be very powerful to understand what symmetries functions have when we go to perform analysis of those functions, which we'll see later in the course. A useful description of functions is to look at their symmetry for both positive and negative x values, such that if f of minus x is equal to f of x, we would refer to this as an even symmetry, or indeed an even function. If we visualize the graph of an even, we can see quite clearly that it is a symmetry by reflection through the y-axis. Alternatively, if the symmetry is a reflection through the origin, we refer to this type of function as having odd symmetry. Finally, let's look at how we can describe functions as continuous. As the name suggests, a continuous function is any real valued function which has no infinities and whose graph does not have any breaks, i.e. discontinuities. An example of a discontinuous function is tan of x. As we can see using the graph of tan of x, it goes to infinity at odd multiples of pi over 2. In the example shown here, we have indicated the points where the function goes to infinity using these vertical lines or vertical asymptotes. And in this example, we have two vertical asymptotes defining the position pi over 2 and 3 pi over 2. Let us finish with a checklist of the video. Here we looked at initial methods in describing functions. Firstly, we should understand what a function is. That is, it's a unique mapping from some domain to range. And we should be able to recognize and state what the domain of range is for different functions, either as inequalities or via set notation. We should be able to identify basic types of functions, such as explicit functions, implicit and parametric functions. We should be able to identify the basic symmetries of functions, such as whether they have even or odd symmetry. We should be able to check if a function is continuous, and if not, locate any discontinuities. And finally, we should be able to derive inverse functions in order to map from y to x as opposed to from x to y. The content of this video is, of course, just to get you started. Your own private study will involve copious reference to your textbook and solving and practicing the problems set for your homework.